Thanks, boss. Thank you, Bob, for the wonderful introduction, and thank you for all for coming out on a snowy night in pursuit of some of this work. I was just using your tax dollars down in Florida a week ago, and it was a little bit warmer down there. But I'd just like to stress as I start this, the little disclaimer off in the corner here that you may or may not be able to see behind the podium is that this talk definitely does not represent the views of the United States government or the University of Alaska Fairbanks, the Geophysical Institute, the Wilson Alaska Technical Center, UAF, anybody else, not even GTIC, not even his views. But so these are my views, and I'll proceed here with a clicker to the talk. This is something that, frankly, I was a little bit unaware of some of these things, even when I had been doing this for, I guess I've been doing this kind of work for about coming up on, 20 years now almost, with a great group of people up at the Geophysical Institute and kind of scattered all over the planet. You'll get a chance to see a little bit of that here. But before we get there, there we go. Okay, so here's the abstract of the talk, what I'm allowed to talk about. It was redacted a little bit, but I'm sure you can get most of this out of it. It's that's the other thing about this talk, is that everything here is in the public domain. I don't have to kill anyone at the end of it, so you can all walk out of here with all the information that you get. This is all publicly available, and it comes from some interesting sources. In the line of work that I do, and there's several of the folks who work with me here out in the audience, between staff and faculty and graduate students, so you can harass them later about the real story behind some of this. But first, a little bit about what the talk is and is not. It is not about environmental impacts. That's the Department of Energy's legacy management is what they call it. That's out of Grand Junction, Colorado. You can ask them questions about impacts from past testing activities, et cetera. This isn't that. It's not Operation Plowshare. I'm not Dan O'Neill. I'm not gonna read Dan O'Neill's book to you, The Firecracker Boys. Great book on the start of some of the environmental movement in Alaska and kind of what went south about Plowshare, although I'm gonna talk a little bit about it. The other thing is, I'm not gonna give you a rundown on the national defense strategy or the efficacy of deterrence in the modern age. That's not what this talk is about. What it is gonna be about is Alaska's one and only test site, and it's one of the few sort of domestic test sites in the United States. It also has kind of a neat claim to fame that I was unaware of as well. That'll segue into kind of a move towards rationality, and that is, how do we maybe stop some of this stuff, or at least limit it, or partially limit it, as diplomats have called it over the years. And then, what does UAF have to do with all this, and why am I talking to you about it? So again, thanks for coming out, and let's leap into it. Okay, when we talk about nuclear weapon states, you typically think about the United States, Great Britain, France, Russia, People's Republic of China, things like that. The most recent one who keeps getting on the news for it is our friend Rocket Boy over in the Democratic People's Republic of Korea, or North Korea as it's called. And those are the nuclear weapon states. We're going to talk about a little bit different view of those nuclear weapon states, and that is the ones in the United States. So, New Mexico got patient zero, or the first of all nuclear tests, and that was Trinity, the Manhattan Project, and that is at Alamogordo. There's also a couple other ones there, Nugget and Crosstie, which were out near Carlsbad Caverns. And those were tests that, actually the Nugget test did a little bit of science. It was a relatively small yield test, and they were looking at radioactive isotopes for industry and medicine. They were also looking at the energy production that possibly nukes could be used. An uncontrolled fission reaction could be used for steam generation. So that was one of the real sort of science tests. Crosstie was actually an early fracking experiment. It turns out in the 60s that before we did hydraulic fracking, we decided to use nuclear weapons to do it. So it's a lot of natural gas exploration going on with nukes. We don't do it anymore, so I guess it really didn't work out all that well. The next one is Nevada, it's frankly easier to name where they did not test in Nevada. Nevada had the bulk of the testing because of the former Nevada test site. They renamed it, now it's the Nevada National Security Site. Guess what? They still do testing out there. Not nuclear testing, geez. Next one, Mississippi. This is one, a lot of people don't really know about these two. Whetstone and Latchkey, the two operations. By the way, if you go to look at this stuff later, what's listed here are the major operations. Like for instance, Whetstone, it had a number of tests under it. It's actually salmon and sterling were the two from Mississippi. But these were very small tests that were designed to look at detection of possible evasive testing, which is actually, this is back in the late 60s. Heck, I think I was born around Whetstone. Is that is one of the key issues today is what if either like peer or near peer ally or enemy, like Russia or China, there are near peers, or a smaller state like DPRK or Iran, especially if they try and conduct a test and try and conceal it. How easy is it to detect? That's what we're going to kind of get into a little bit on this. Colorado had a couple of its own, and this is my only sort of line about Plowshare and Edward Teller's mania about these things are useful for everything, is that when all you have is a hammer, everything starts looking like a nail. So, hey, I got nukes. I bet you we can use a nuke to do that. You got a problem? I'll use a nuke to solve it. These two were actually more natural gas fracking experiments, except what these were designed to do, they were trying to look and see if they could create an underground natural gas reservoir using a really, really big firecracker. Again, didn't really work out all that well. And then the last of them is that Alaska had its own tests under Flintlock, Mandrel, and Grommet. And these were out in the Aleutians. And this is something, actually, that I remember sitting at a meeting, and I was sitting with a guy, a contractor who worked with us. It was actually who you were talking about the other day, Guy, with the tattoo. It was Dave Carlson, the retired Air Force colonel, and I remember talking about something, and he goes, oh yeah, I was at that test. I was in the tunnel when they laid the device down. So this is a guy who had gone from the active days in the Air Force when he was doing testing, and now was working on the, hey, let's kind of stop this testing stuff. So people can come full circle. All right, click. So out here is the grand view of Alaska. You're all sitting somewhere up near the little marker on the Google map there. And this is the Bowers Ridge out in the Aleutian chain sticking up off it. And if you follow that, you come down here to the Rat Islands. And that is where they did the testing for the 60s and 70s out at Amchitka Island. So just to give you a little perspective out here, these are the rats out here, and actually I can hardly see it, but so this should be Attu, and then Shemya is here. We actually have a station out there at Shemya. And then just a little bit off of where Amchitka is Kiska. So Kiska and Attu, as you might remember, are where the Japanese actually did land. This stuff has nothing to do with that. These came way after the Japanese were gone. Because it was kind of funny as I was doing a little bit of background on this, we actually did invade Amchitka, but no one was there when we invaded it. So it was kind of a good one. So there's the rats at the end of the chain. This is Amchitka Island where the nukes were set off. This is Kiska up here, and then there's Attu, and then that one of those little guys there is Shemya where we have a station. Spent some fun time, quality time there with, well, I'll keep talking about Guy during this talk. But spent some quality time out there putting a station in as part of this work as well. So Amchitka is about a 30-ish mile long island. It's never really been inhabited, but people would stop there occasionally, indigenous peoples, as they were traversing throughout the Aleutians. If you've ever been on some of the Aleutian Islands, it's just, the first time I went out to Shemya, you see pictures of what the airstrip looked like in World War II before there were buildings and mess halls, et cetera, and it's just tents. And the temperature's perpetually 40 degrees and raining outside or snow or both. They're just kind of they're gorgeous looking places, but I'm really not sure I'd want to live there. visiting is fun. So at any rate, back in the 60s, the then Atomic Energy Commission, which led to the Department of Energy, came out there. They used an existing road called Infantry Road out there and looked at this for some testing for the shots. And those shots actually were Longshot was the first one, Milrow was the second, and then Canakin was the third. And Canakin was quite a big one. So these are not the same things as the idea for the artificial harbor that Dan O'Neill talked about in his book, the central thesis there. These were actually weapons tests. These weren't the sort of peaceful side of things. These were definitely the pointy end of the spear kind of tests. So Amchitka Island had a series of 3 tests conducted on it. Longshot was the first in October of '65. It is it's a relatively big thing. 80 kilotons is not a small thing. We're talking yields an equivalent of TNT. So it is and by the way, when you're looking at this, like an 80 kiloton device is a fission device. It's relatively small thing. It's not a thermonuclear bomb. Those fission devices, they limit out, you really can't build them too much bigger than about a megaton. And people have tried. So that's about an upper limit on those things. You got to start going to hydrogen bombs if you want to get bigger, and then you can start building them really large, up to like Tsara Bomba that the Russians put off over Novaya Zemlya, which was like 200 megatons. But we'll get into some of that other stuff later. So this thing was a calibration shot for discrimination. And when I say discrimination, it's part of the challenge of how do you discriminate a nuclear blast from an earthquake? These days, in some scenarios, it's like, well, that's really easy. You just watch CNN and then they tell you when DPRK is going to light one off. So there's other forms of getting information in, but it was done following a natural magnitude 8.7 earthquake that was nearby. There's some evidence that may have just been a really, really lucky coincidence. It wasn't like they were waiting for a shot. However, waiting for a magnitude 8 in Alaska, you might have to wait a decade for one of those. Waiting for like a magnitude 4, just wait in 5 minutes and you'll have another one of those. So it was used for discrimination. The next one was 5-ish years later, and that was Milrow. This was a megaton, and this was a thermonuclear weapon. And it was designed as a safety check. So you light off a megaton firecracker just to test if it's going to be safe to light off a bigger firecracker. So the thing behind this is, and by the way, just in case you want to know what these numbers are, this is the depth of burial below ground surface, and this is the rough magnitude of the body waves that were the seismic P waves that came out of it. So a magnitude 6 earthquake equivalent for this thing. And you might be wondering why an 80 kiloton and a 1 megaton, and then when I talk about the next one here, the big guy, magnitude 7, they're all about the same magnitude, but tremendously bigger yields. The deeper you bury it, the weaker the P wave result on the surface. There's the relationship that goes as like the cube root of yield, and it has to deal with the depth of burial, which I'll talk about a little bit more. So the Milrow shot was actually a safety check for Canakin to make sure we could do it. And this is, here's our claim to fame, the largest US underground nuclear test was in Alaska, and this was the Canakin shot. And the reason why it was done up here, because apparently Nevada got shaken up too much by its previous testing, they decided it wasn't safe to do it in Nevada. So that's why they were looking for alternate sites to move a large one. Because as we talk about the treaty stuff, this is after a moratorium had passed, which I'll talk about in a few minutes, and after testing moved underground. We weren't blowing up pretty firecrackers in the sky anymore. So this is a couple of shots of just what Canakin looked like. In case you're ever wondering what a W-71 warhead looks like, that's one of them. This is a nice Spartan missile. So the Canakin shot testing this is with that warhead, which was designed by the Lawrence Livermore folks, and put into this warhead, or missile for the Air Force. This thing wasn't designed to go attack China and go down through the Earth. It was actually meant to go up into space and detonate at a relatively low altitude, saturate the ionosphere with X-rays, and destroy the re-entry vehicles for a MIRV that was coming in from a hostile. This was part of the Star Wars program and the anti-ballistic missile program. So that's what this was designed for. They're just going to lower it down because I guess it was easier to drop it in pointy end first in a mile deep shaft to do the test. So we weren't testing in the atmosphere anymore. In fact, there was a treaty banning that. So we were testing down below the surface. So this thing was a 5 megaton shot. What I'm going to show you here is how the seismic waves were detected from a much smaller shot, and that was from Longshot, the first one. So Longshot was set off. It was only 80 kilotons, about 62 times smaller than the Cannikin shot. The first trace up there, this is from a paper by our British colleagues at AWE Blacknest. That's from Yellowknife in the Yukon. Then the next one is a station right next to the Blacknest site in Scotland. And then it moves out along to, this is in Great Britain, this is actually a site in India. And then this one is in Warramunga down in Australia. So these are a little bit filtered, so they got rid of some of the background noise, but even for an 80 kiloton shot, which is not a small nuclear weapon, worldwide you can detect these things. So they move out for quite a long ways. So big tests, generally not that hard to detect. No one on the planet's going to get away with shooting off an 80 kiloton thing without somebody knowing about it. That's pretty easy. In fact, you could probably buy a Raspberry Shake online and put it in your house and detect one of these things. That wouldn't really be all that hard. So we'll get into some of the challenges, but first, that Cannikin shot. Just what's a sense of how big is a 5 megaton firecracker? This is just the scary part of this work is that, okay, here's a little thing, and this is gonna be great because I gotta go to DC next week, and I'm probably gonna be on a freaking watch list because I showed this that Eielson Air Force Base is gonna get nuked. So I'm doing it conscientiously because you wouldn't hit a civilian center like Fairbanks or North Pole, you would attack a military target. So what we're gonna do is we're gonna kind of repurpose that W-71 warhead. It was actually, when I say that it was designed for anti-ballistic missile, they actually lined the thing with gold as a tamping material to help generate extra X-rays and minimize sort of fallout effects. So I'm gonna repurpose it to try and vaporize Eielson, and like I said, I'll probably won't be working at the GI next week, Bob, so. All right, so at any rate, we're gonna drop it, and what we're gonna do is we're gonna optimize it for doing the damage that we wanna do to Eielson Air Force Base, and that is I wanna basically vaporize most of it. I don't wanna maximize fallout because, Russia's pretty close here. Not saying that Russia would do this to us, but just someone's gonna do it. And there's what the blast looks like. So, and I detonated it at 3 kilometers altitude, so just under 10,000 feet. And that was to optimize some of the effects for this. If you want to play with things like this, there's fun online calculators that you can do for this. Way back when I was at the military academy, I did take a course in the physics of modern weapon systems, and these were the kind of problems we got to play with. So everything in this little green circle here, that's a 500 rem dose. You're pretty much dead from radiation there, which is kind of a secondary concern because everything inside this thing pretty much gets vaporized. So you're not only dead from radiation, you also just got vaporized. So you're kind of screwed no matter what. Everything out here, you're probably also dead. That's heavy damage where buildings are destroyed. There's instantaneous fires that are set. Out to this radius, this is what is moderate damage. In other words, some of your buildings might survive. I just wouldn't be near a window or a wall that was less than maybe 3 feet thick. This is where you might get 3rd-degree burns if you're in line of sight. So that's a long ways out. Sorry, North Pole, you're probably gonna get toasted. But don't worry, everybody, we're safe. We're up there in Fairbanks, so everything's gonna be just fine where we are. The outer ring there is where light damage is gonna occur. So even this was 5 megatons. 5 megatons at 3 kilometers altitude. Just to backcast to my youth there, when we did that class, we also did one where we had to optimize the problem for you have to use the smallest number of nukes and take out all the electronics in the United States. And I'm trying to remember, yeah, it wasn't classified. It was 4 at about 100 kilometers altitude, spaced over the continental United States, and you pretty much wipe out unhardened electronics. So the EMP, there's ways to do that as well. But at any rate, this is kind of just a scenario where these things they're nasty. I mean, you know, it was kind of scary back in the late 90s when India and Pakistan did their last tests, that I remember seeing a news interview with some folks across the Kashmir where the border was, and they talked about how, a nuclear war, you know, with a limited exchange with relatively small weapons wouldn't be that big a problem. That's just a really scary attitude, because I mean, this thing, yeah, we didn't get blowed up in Fairbanks real good, but we're not really going to want to live in Fairbanks anymore, or pretty much anywhere in the state. And that's probably not the only one that's going to be inbound in a scenario like that. So it just fades to black, and it's a kind of ugly scenario, but now we go to the happy part of the talk, and that is about how do we kind of constrain or contain this madness. Now, like I said, this talk really isn't about deterrence, but that has been sort of the modus operandi for the past 60 years of the, 70 years almost, of the global powers, is that, hey, if all the big guns have these things, they're sane enough not to use them on each other. Hey, so far so good. In fact, still, we are the only nation on Earth to use nuclear weapons in combat. We're the only people who've dropped them on anybody else. Everybody else has just tested. So we are not absolutely without guilt, although I guess most of us probably weren't born then, so we didn't decide to do it, so you can all sleep well tonight. All right, so nuclear test bans. That's kind of the area that me and the group that I'm fortunate enough to work with, that's what we deal with, is how do we look at these various bans. So the US and the USSR just bilaterally, without any kind of treaty, just entered into a moratorium of testing between 58 and 61. They just stopped. Now remember, prior to this, all of the tests were in the atmosphere or at the surface. No one was putting them underground. And if you go look at some of the pictures of these things, it was when we were, they talk about people in Nevada being the downwinders. Well, the Army was also putting troops on the ground to see, hey, how can they deal with dealing in an environment like this? Again, not really all that nice. So the moratorium ended during the Cold War, and then they started to go to these peaceful nuclear explosions, the PNEs. And this was Operation Plowshare. We did 27 tests. There were more than 27 explosions. The Russians did a heck of a lot more PNEs than we did. And when India tested its first nuke in '74, they said that it was a peaceful test. Most people think it was probably a weapon, but whatever. At any rate, the PNE stuff kind of went away. It's not really easy to contain the byproducts of these explosions, so it's a little bit tough. And then I'm going to talk about these three treaties, two of which are still in force and abided by the United States. And then this is the one where we do most of our work on the Comprehensive Nuclear Test Ban Treaty, although it is not in force, but I'll get to that in a bit. So I'm going to kind of whip through the history here. This is President Kennedy signing off on the Limited Test Ban Treaty, which was a tripartite agreement between the US, the USSR, and the UK. And it was that essentially no more atmospheric, no one's ever really blown one up in space. They've kind of done it in near space, like the Starfish blasts, and no more underwater testing. Underground testing, however, is totally fine as long as the byproducts from it, namely the leakage from the explosion, as long as it stays within your state territory, you're okay to do underground testing. So this is when things moved underground. And it came about, it was started in 1958 when that moratorium started, which was voluntary. The US broke it first, and then the Russians broke it next. I think the US went in '61 and the Russians went in '62. So we all started testing again. We said, hey, this is madness. We need to put them underground. Key thing here, the national technical means of verification were how it was enforced. Now these things are the national technical means, the group that we have, we're part of that. Also some other folks from the Air Force I'll talk about in a bit. That's each country's means of verifying that another country's not doing stuff. These are generally not public, what the capabilities of these are, and they're not available to other countries. The challenges with verification precluded this from being limited to comprehensive. In other words, it's limited, we're gonna contain the size, well, actually not sizes on this one, that comes next, but we're gonna contain where they are, we're gonna do them underground. So that led to the Threshold Test Ban Treaty, which it started in '74, but then they realized, us and the USSR, former Soviet Union, because this was a bipartite agreement between us, was that we weren't really sure we could verify the treaty. Because this one limited things to under 150 kiloton yield. It's all still underground. It waited for 16 years to go into force after the JVE, the Joint Verification Experiments. So this is the kumbaya moments here. This is the Nevada test site where you got a Soviet and American flag flying side by side in '88. This is over at one of the test sites in what is now Kazakhstan. So the guys in the white hats are not the good guys, those are just the US dudes. And the guys in the red hats are the Soviets. So we did 2 experiments. This was Kearsage, and I forget what they called this one over here in Kazakhstan. But we took our nuke over there, blew it up, and vice versa, and looked at the results. And there was quite a discrepancy in the blast, but what it did was it set up the ratification 2 years later where we realized, hey, the Earth plays a role. We don't know as much as we did, even for relatively large blasts. We need to do more R&D towards the National Technical Means of Verification. So, and the work here led towards what is almost there with the Comprehensive Test Ban Treaty. So this is the thing me and the gang that I've been dealing with have worked on for the most. There has been a quasi-effective moratorium on testing because most countries stopped. Soviet Union last test was in '90, the US in '92, UK '91, France and China, this is classic. They tested, then signed the treaty. So they did their last test and then signed in '96, same year. India and Pakistan in '98, and then North Korea, their last one was in 2017, so we really haven't stopped them. This treaty was signed by President Clinton in '96, but was not ratified by the US Senate by like a couple of votes. So it is not entered into force because we are one of the nuclear possessing states, whether you have nuclear reactors or whether you have weapons. Those 44 countries have to sign and ratify this treaty for it to go into force. This puts us in great company. Here's the US, here's the Islamic Republic of Iran, Israel, China. We've all signed it, these 4, but have not ratified it. And they have to ratify for it to go into force. The underlined ones here, this is DPRK, this is Pakistan and India. They have not signed or ratified, and they have to do. And in fact, one of them is still actively testing. Big difference here, the technical means are no longer national. They're available to all states parties. So the data from this treaty is available to all the signatories. So it's technically not available to those guys because they haven't signed, but we share data among ourselves for these countries. Stations in China we get the data from, stations in Russia, vice versa, they get the data from our stations as well. This one aims at a ban on all nuclear testing. So hence the Comprehensive Nuclear Test Ban Treaty. We'll see, this thing's been open for signature for quite a while. Maybe not. That's the building that they work in there in Vienna, on the upper floors of that one on the right. It's a UN center there. So at any rate, the verification regime for this treaty is seismic. And the primary seismic stations are used to detect the blast, and the auxiliary seismic stations, which are existing networks of national stations, are used to help locate where the blast was. Important challenge. This is one of the sites out at Pinyon Flat that University of California, San Diego runs for us. And the other technology is RadNuke, the radionuclide part. This is where the radioactive particles and gases travel on the winds, and that's the smoking gun. That's how you differentiate or discriminate between them. This is the site run by General Dynamics out at Midway Island. We have an infrasound station out there as well, which is the next technology. And that is the acoustic part. This is a view of our one of our arrays down in Windlass Bight, Antarctica. I am actually in that picture. And back when they allowed me to go to the field and touch stuff. Clandestine atmospheric test is where you'd get that stuff from. And this is really low frequency sounds that propagate a long way. The reason I'm standing here is because this is in the treaty, and that's how this got stood up, is that none of the big powers like us or the Russians or the Chinese or the French or the UK would pony up their satellite data, which is part of the national technical means. They wouldn't put it in under the treaty. So we needed another way to look at atmospheric tests. Infrasound came back from the dead after sort of fading out in the 1980s, and now is actually a really strong going concern. But go back 12 years to when I gave the Science for Alaska talk on infrasound, and you can see what it's all about. At any rate, the last one there is hydroacoustic. No one's doing this these days. This would be for an underwater test. It's hard to get a picture of one of these things because like a site out at Diego Garcia that we've been to and we kind of got somewhat involved with, this cable is almost 150 miles long. So these things are huge and they're bloody expensive. To lay these cables, to put a cable laying ship out there, it's like $150,000 a day. And that's from when they leave port to when they get back to port, not just when they're doing the work. So really expensive stations, there's only a few of them because sound travels well in the oceans. But that's the regime for verifying that people aren't testing. This is what it looks like on a global scale. We run a number of these. So you're gonna see another one of these maps, but you can see these various kinds. Here's the seismic kind that are primary, the ox-seismic in green, the infrasound in the magenta there. Yellow is the hydroacoustic, and the RadNuke, both laboratories and stations, are these other red and amber circles there. So it's scattered all over the planet. About 85% of this is actually deployed. So it's there, it's working, the data's available. A lot of that data is publicly available too, and a heck of a lot of good science comes out of that data, as well as the treaty stuff. It's used to help with mitigate tsunami disasters, et cetera. It looks at bolides, which are explosive meteors that come into the atmosphere. It's used for a whole bunch of different purposes. The final part of the verification regime is on-site inspection. And these are just scenes from an exercise in Jordan, because North Korea really doesn't let the treaty organization go in and do on-site inspections. After a suspected test, this would be the final means of verification. Back during the Bush administration, when I first started doing this, during Bush W's, we were actually told to get up and leave the room at meetings if this was discussed. That's how low tolerance they had for on-site inspection. However, at the same time, they said, yes, we support your work running the stations, happy to fund you, but if they talk about OSI, get up and leave the room if you want your funding. That's a fun thing for me to do, to tell other academics that I'm funding that they have to get up and leave a room. So at any rate, still talking with those guys. All right, every field has that one slide that everybody shows. This is from Bill Walter at Lawrence Livermore National Laboratories. It's just a thing of beauty to behold. This is everything that could possibly cause a signal, either real or clutter, in other words, a false alarm, if you're trying to detect nuclear weapon tests. And granted, everything's going on underground right now, so that's where most of the stuff is. But there's a lot of other commercial activity, like mining blasts, et cetera, that mimic this. There's accidents in terrorism, like gas plant explosions, that can mimic a nuke going off. There's a whole bunch of false alarms. And like I said, the problem these days is that as tests get smaller and smaller and smaller, and people might try and do an evasive one, that's where this becomes a real challenge. Like I said, trying to find an 80 kiloton test, no way. The off-the-books threshold for that Comprehensive Nuclear Test Ban Treaty is a 1 kiloton burst. It's actually really difficult to make a 1 kiloton bomb. To make a small fusion device is even harder, but a lot of great artists are insane, so people try and do it. All right, so anyway, this is kind of the whole sort of schmear, including those atmospheric explosions, which we pick up, which aren't nukes going off, it's just meteors striking the atmosphere. However, they have some of the same optical signatures, and they estimate the yield, the optical yield in megatons for those things. So there's lots of clutter out there and a whole field of science that goes to trying to mitigate the clutter. All right. There we go. All right, so how do we verify these treaties? We have to detect a blast. We have to localize it. We have to discriminate it, as in, was that blast what we think it was? And then we have to estimate something about it. So all these things go to detection. That's like, hey, something happened, we need to find more about. The location goes back to, was it at a known test site? Or if it's tested somewhere else, it's like, well, hey, that helps towards what's called attribution. It either helps us prosecute if it's a criminal act, or it helps us, say, where do we send the thank you card when we retaliate? So discrimination is, was it just a chemical explosion? In other words, we did tests out in the Negev desert with 10, 15, 80, and 100 tons of TNT. So up to 0.1 kilotons. It was just used chemical explosion disposal. But those things were detected, regionally over long distances. So it's well below that 1 kiloton threshold. But there the thing is, how do you discriminate? Well, you can use rad nuke to do it. And then estimating the yield, another big problem, because that can go to design issues where what if one state decides to test something in someone else's territory? So location doesn't always do it. All right, so that's the questions I was just answering there. Where did it occur? Was it a nuclear explosion? So here's the only quiz you're gonna get tonight. These are, sorry, gotta go back one. My clicker's freaking out here. All right, so I'm gonna put that down so I can't do any more damage. All right, these are 3 traces that are all from the same station in Pakistan. They're from the Nylor station. One of them is a genuine nuclear blast. 2 of them are earthquakes. Okay, so one of the earthquakes should be really easy to pick out because it really doesn't look like the others, okay? The green one, right? But if you look at these 2, background noise, sharp onset, that seems like an explosion. And then a coda of some kind. Well, these 2 are, one's from an earthquake and one is the 1998 Indian test, which was like a 20-ish kiloton thing. Nuke, earthquake. They look very, very similar. And the deal is that region, unlike the Nevada test site or Novaya Zemlya, that Russian island, or the Kazakh test site, or Lopnor, the Chinese test site, not well characterized seismically for explosive events. And relatively small yield, difficult to do discrimination. So that's kind of like the holy grail these days is, can you find smaller explosions like that? So how do we do this stuff in the United States? Well, good old Dwight Eisenhower appointed the Army Air Corps about 2 days before it wasn't the Army Air Corps and became the Air Force, said, you're responsible for detecting the release of nuclear energy anywhere on the earth, water, land, space, etc. And I really have no idea, I got this slide from somebody else, and I have no idea why it's unclassified, because it kind of looks like, if you look at this in the better screen, it looks like Dwight's kind of a ghost there. Maybe they declassified the fact that he was actually a ghost. So this comes from our friends at the Air Force Technical Applications Center. They have a really nice base down there at Patrick Air Force Base, where I just came from, actually, in Florida. Really nice big building, and they have one of the best mottos I've seen. So that's in the floor of their building. Now, this is a great motto. These guys, we actually work with these folks down at Eielson Air Force Base, Detachment 460. AFTAC it's called AFTAC for short. These guys we work with in our lab. They have that version of the motto, except theirs is in Russian, because as they say, we used to be Russia here. So AFTAC is the one who runs the U.S. Atomic Energy Detection System. This is that national technical means for the United States of America. Some parts of it are not publicly available. Other parts are. They have stations that run in support of the Comprehensive Nuclear Test Ban Treaties International Monitoring System. So do we. So we work with these guys. They also have satellite assets, because again, that's part of the national technical means. Like, actually, a graduate student from the GI took over the program where there's 2 antennae sticking off of every GPS satellite that do nuclear detection monitoring. I mean, this guy is like straight out of grad school. First proposal he writes is for a 20-year program and gets funded. Of course, wasn't going to go to anybody else, and he was working at Los Alamos, so it's the one proposal career. That was pretty cool for him. These guys also, usually you have to wait for radioactive particles to drift towards you. The Air Force isn't that lazy. They go fly into it with the WC-135s. They have a couple of them. They're called Constant Phoenix. It's essentially a rad nuke detector on a mobile platform. You fly it towards where you think the plume's going to be. So this challenge of low yield testing detection isn't really new. This is a seismograph during one of those shots in Mississippi. And this is when, the Atomic Energy Commission was not keeping all these things secret. Locals were getting involved with this. They were building their own seismometers out of chestnuts. And these are shots from the Mississippi archives from one of those tests. This is from the Sterling shot, where that's the actual trace from the Sterling blast, which was very small. It was only 0.38 kilotons, so less than a kiloton. And what they did was, this 3 kiloton blast was in a salt mine. That hollowed out a chamber. They suspended this one in the middle of it to try and conceal the test. They didn't try and conceal it, really. What they did was they advertised it publicly, so people were putting chestnut seismometers out there. And I guess, can you guys read that? It says, "Seismograph, please do not eat." So she was just going to wait for the things to tumble over. So I guess that didn't come out too well. But this is part of the VALA uniform program, which was looking at evasive testing. So it's kind of an old idea that people knew about this. If you went to my talk in 2008, you'd see this slide, and that is, Buck Wilson had sensors out at Stevens Village, out near Fort Yukon, and at Lop Nur, a 20 kiloton cratering test goes off, Cheech 12, from the Chinese. The acoustic waves from this travel around the planet, take 13 hours to get to Stevens Village and are detected, going the other way around the world and coming back over the side 24 hours later. That's what that paper recording is at Stevens Village. So one of my colleagues who's not here, he's actually doing volcano work in Hawaii right now, gives me no end of grief for showing this slide, because he says, people think that we still use paper traces and put them on light tables and correlate them. Well, what's really funny is that David has it coming to him, because right now he's funding people to digitize paper records from Kazakhstan. And in fact, last week I was at a meeting where not half the talks, maybe a quarter of the talks were about digitizing old paper records of old explosions. So there's still a lot to learn from these things. This is why the comprehensive test band doesn't have satellites, is because you can do it with that. So I am actually getting wrapped up because I'm stealing your question time here. These are some of the more modern things that I show for David where there are no paper traces on here. There's very high-speed scientific things being done here. There's a paper I wrote about how to locate very small blasts in a place like Baghdad or something using a space-time approach. This is some things that David does with some of his grad students for looking at waveform synthetics and comparing them to real data. The top center there is that Cyrene test where it was the 100 tons of TNT going off. Colleague David was the lead author for the international community on that. This is one of our infrasound arrays in Fairbanks. It's my favorite. It's Bob. We didn't name it after our director. It's the big orange box. This is down in Antarctica, which our crew just got back from relatively recently. Here's me doing my non-science role, standing and staring at a box with wires in it on Midway Island. Green is good, means our stations are operating. That's what I get to do these days, is report to higher about things like that. So this is what our group does, and in case you didn't notice the little logo on the rest of the slides, here's the big plug. We are the Wilson, Alaska Technical Center. Technical comes out of the National Technical Means, because that's what this was founded to support. And we named it after Buck Wilson, who spent 50 years working at the Institute. So we named this after Buck. And we're hosted at the Geophysical Institute at UAF. We have a bunch of faculty, staff, and students that are just a world-class team helping us out with keeping this going. We took over this program from the University of Mississippi back in 2008, and it's only been just getting bigger and stronger, where we started with 2 stations, now we've got 23, scattered all over the planet. So the red ones are the ones that we have contractual responsibility for. So they're kind of scattered. And I have been to a number of these without breaking them. And some of them I've been to where I did break them. Haven't gotten down to South Pole yet, but I've been out here to Diego Garcia. The blue ones are some of the US Atomic Energy Detection System that the Air Force runs, and we actually work with them kind of closely on some of those stations as well. So our little group kind of goes all over the place. So thanks for paying your taxes for our frequent flyer miles. Unfortunately, we don't get them when we're on military aircraft because several of these places, it's mill hops only, so wish we got them. Meanwhile, I'll kind of wrap things up here with some recent events, and this was the 3 September 2017 test. It was the one that Kim Jong, said, hey, it was a hydrogen bomb. No, it really wasn't, but that's okay. It was a big one. I mean, it was over 100 kilotons. The error bars on this are really large. It's somewhere between 70 to 200 kilotons, but 140 is kind of the answer these days. I can only imagine the conversation he's having with them. It's like, does this end go forward? No. Exalted leader. It's the other one. So one of the real challenges here is that, remember how those very different ones at Amchitka all had kind of roughly the same magnitude? Depth of burial is a really big thing. Where we did a lot of our testing out at the Nevada test site, it was relatively flat. We did test a little bit under ridges. Mount Mantap is tremendous. So these are the tunnel entrances, the adits, and those are all 6 of the blast sites for those 6 North Korean tests. If you're off by a little bit in your estimate of where those are, you have like 100 or 200 meter difference in the depth of burial. The error bars get really large on what the yield of these tests are. And the North Koreans really don't let us go check out their site. What is nice is that the one near North Korea 6, INSAR data, like those dishes you see on top of the Geophysical Institute, synthetic aperture radar looked at surface depressions, so we were able to relatively well constrain where those things were. So we're getting better at it, but the problem is their earlier tests were relatively small. The error bars are all over the place, and the weapons designers like to know what the yield was because there are certain thresholds for certain designs that let us know how far are they along the path of getting to bigger, better, stronger bombs, which we'd kind of like to keep them from doing. So this is from the Alaska Earthquake Center. No, this is not where North Korean missiles can go to. This is just the path that seismic waves would travel to get to various stations that AEC monitors. So for that September blast, remember, the Earthquake Center is not tasked with finding the release of nuclear energy. That's AFTAC. But 20 some odd minutes after the blast, they had a stable magnitude estimate and a stable depth of burial. And these are right on par with things that have been done for 6 months of analyses. So AEC, even though it's not tasked with it, it's tasked with monitoring natural hazards, can also do a pretty damn fine job with some unnatural hazards as well. And just to give you an idea of how the waveforms moved out, these are some stations in the EarthScope mission across Alaska, and here's that blast moving across. One of the stations near Juneau must have been a parade going on. It's kind of noisy. So the rest of them really, really clear for how that goes. So the last thing I will talk about for a few seconds is that, as Bob mentioned, we got sort of the nexus of it was our group in WATSE, the Wilson Alaska Technical Center, got recognized for the work we were doing by the Department of Defense, and we became a university-affiliated research center. So if you think UARC, what they're abbreviated as, is that it's kind of like a national lab. What we can do is we can avoid sole source competition rules in the national interest. So national laboratories can get direct funding from both Department of Energy and Defense to do critical mission stuff. We can do the same now. So this is kind of like a golden goose for UAF. This is a big, big deal. We're only the 17th one formed. We're the only one formed within the Pentagon. We're under the Assistant Secretary of Defense for Nuclear, Chemical, and Biological Programs. So we're pursuing that. I'm not only the director of the Wilson Alaska Technical Center, I'm also the executive director of this thing. So there's some of what we can do. We're trying to get Bob McCoy offensive capability with that rocket outside the GI. It's basically what the GI does is kind of our core competencies, and then we apply these to problems of non-proliferation and monitoring. So I'm sorry I took some questioning time there, but I am happy to. And what I'd like to do is acknowledge a few people. Bill Walter at Lawrence Livermore, Alan Poffenberger at AFTAC, Mike West at AEC, and then that group of folks who work with us at WATSE. And I didn't put the grad student names down there because I couldn't remember who was really funded by WATSE and who wasn't. But I think, Jordan, you're funded by WATSE, aren't you? All right. So, at any rate, I'm really privileged to be able to work with these folks, and thanks for your attention. That is it. I'll be happy to answer questions.